All right, shall we get started? My name's Tom Arthur. I'm a founder and CEO of Dianomic, and today we're going to talk about Project Fledge and FledgePOWER. So just quickly before I dive in, how many people have heard of FledgePOWER or know what FledgePOWER is? Oh, well, that's encouraging. I'm kind of happy. All right, well, I'm going to have a little bit of fun with this presentation in the first 4 or 5 slides, because what I'm going to talk about mostly today is data management. And what is data management, I've learned, is defined a little differently by IT than OT. And I'm going to give it more the IT bent, and I'm going to try to apply that to OT problems, and we'll see if I succeed or not. So I'll call this unscrambling the eggs. And I'll look at the queries here. And if you start with scrambled eggs, let's call that your data lake, and you dump all your data in there. How many of those questions can you answer? And if you just look at those queries, where do you have to go and where do you have to start managing data to even be able to answer those questions? That's absolutely true in machine data. That's absolutely true in OT data. And it is a massive problem in building any kind of ML product, any kind of digital twin product, any kind of unified namespace product, any kind of name sharing or security or data sharing project where you need to authenticate and do data lineage. You can't do them if you don't start with a smart edge, period. So where you begin data management actually matters. You can't just throw everything in a data lake and answer an awful lot of questions. Now, what is data management? And here's more the classic IT perspective. How many people are familiar with like Snowflake or Databricks? All right, so this is basically plagiarism right from both of those companies when they start describing their businesses and what they do in data management. So if you just kind of go from left to right, what is data management? It starts with connecting and collecting data. Usually when those companies talk about it, they talk about dumping it into a data lake and then start doing something with it. But from them, it would be any type of data, not just time series data, but array data, vision data, radiometric data. Pick your favorite data type. Type shouldn't matter. Any protocol, any data map. Take any of that data, dump in a data lake, then what? Then the next step is transformations. And so what are transformations? In OT world, you probably start with something as simple as units. Are we all using the same units? They have the classic NASA problem where that team used metric and that team used, regular. This is a big problem in OT that people tend to ignore. But transformations, things like normalizing your data, making sure you don't have duplicates of data, making sure your units all match, it's actually harder than it sounds. And then the next step, I'll call it contextualize. But most people go over it with these big buzzwords now today. So they'll say, hey, it's a digital twin, or it's a unified namespace, or it's a single schema. After I start all these transformations, how do I possibly put all this in context so I can share it with my colleagues? And if I'm going to start sharing data intercompany, like a whole bunch of conversations are today, how in the world do I interpret data if we don't share schemas, if we don't share namespace, if we don't share understanding of assets and attributes? And then after that, the ultimate thing, so if you go read the marketing materials of Databricks, is called curation, right? So they have these 3 kinds of tables ending in the golden table. And the golden table is perfectly curated data that is now ready for the perfect, report. This is now ready for the data scientist to build the model with. So all of these steps are required to then just have the data ready to be used. And then in the OT space, after I have all my data curated and ready, well, then I have applications, of course. So it's an application that's doing ML. It's an application that might be doing some closed loop on some machine back in the industrial factory that automates everything. So I got to take that data somehow, and I got to apply all that back down from the cloud to an on-prem system like a Historian or an MES systems or whatever it may be, all the way maybe to the PLC or the RTU. So this is basic data management that you have to tackle before all of these new big ideas can even be started. And it starts at the edge. But the big problem is OT. And frankly, IT people don't appreciate this. And this is really the OT-IT divide right here, because OT data I'm an IT guy, I'm a network security guy. I've learned all this in the last 5 years, so I really don't understand this really. But I am kind of shocked because I started up in networking, and everything in OT reminds me of networking 1988 when I was selling commercial TCP/IP stacks and had to explain why you needed it. No, DECNet's fine, no SAA's fine, AppleTalk's fine, IPX is fine. You know, there were no data mappings, you know, something like SNMP didn't exist, so there was no semantic model to manage a network. I mean, all that was like brand new 1990, but all of that is OT. It's OT today. So another point is this brownfield, greenfield concept. And if you have just one takeaway from this, brownfield, greenfield is forever. Most people think OPCUA or MQTT Sparkplug is going to solve all this with this new protocol. It won't. And it's really simple, and IT guys don't get it. If I buy a capital piece of equipment, I got a 20-year lifespan on it. It came with a 3 to 4 year lifespan on the compute, because compute is 3 to 4 year lifespan, period. GPUs, CPUs, operating systems, they change every 3 to 4 years. Orchestration, 3 to 4 years. But I got to have this transformer for 30 years. So a brand new transformer today, using 61850 today, with a terabyte of data today, 10 years from now you're still using it, and I guarantee you it's brownfield. So you got to abstract the capital equipment of machines and compute to keep going and compute with the latest and greatest. So brownfield, greenfield in OT is forever. You need to abstract the data from the machine, and that's an intelligent edge. So you look at that, but bigger problems, of course. Most IT people don't deal with millions of real-time streams. They don't even understand what a tag is. They don't understand that it didn't even come with units. And they don't understand that it doesn't have a schema. And they didn't understand that engineering and maintenance and operators think about the exact same tag quite differently. So they fight over what the schema should be. I mean, that's bizarre to an IT person to even think about. And so then you look at things like unstructured data. It's unstructured. What do you mean it's unstructured? You know, Salesforce isn't unstructured. I got MuleSoft, that's not unstructured. But this is all unstructured data, and then the protocol chaos, of course. There's hundreds of protocols. I'll talk a bunch of use cases here where we're just helping people migrate from one protocol to the next protocol to the next protocol, which is the brownfield, greenfield problem. And then, of course, the data definitions. There aren't any. Everybody's different. So how in the world do you take that world and manage the data? And how do you do that if you just dumped it all into Hadoop? Can't do it. You just can't do it. And everything else is noise until you do that. So OT data management is challenging. And really there are 3 areas that you can get it done. And I'm going to call it the edge, I'm going to call it on-prem, and the cloud. Those are really the only 3 places to do these workloads and start managing your data. So you could have an intelligent edge, of course, in, let's say, a PLC, an RTU, or whatever. And of course, those are intelligent machines. But they also tend to be proprietary with their own unique ways. So if you really are going to start doing things like a closed loop, automated machine, think self-driving car, but now it's a self-driving centrifuge in oil processing, you need a way to operate that closer to the edge. So to solve a brownfield, greenfield forever, you have to have an intelligent edge. To do set points and targets, the edge has to be there. You're not going to be doing that from the cloud anytime soon. It might just be a compliance reason, actually. Doing things like reliability, availability, serviceability, security. Security fundamentally starts at the beginning. You can't secure any data that you don't authenticate right at the data source. If you don't authenticate it right at the data source, you don't have data lineage. Are you really going to share data where you didn't actually sign it at the data source, so you kept track of your data? You can't do that without an intelligent edge. And then all these new use cases. Intelligent automation, digital twins, semantic models like 61850, or what SESME is doing with OPCUA5, unified namespaces, ML, AI, or trusted. None of those are possible without a smarter edge. You can't do it. And then there's a whole bunch of data management tasks that the sooner you do it, the better. You could do it in the cloud, but then again, if the longer you wait to take care of a mess, the longer that mess is traversing all of the different pieces of your infrastructure before it's clean, that you have to come back and clean it all up. So if I got simply something, let's say a bad sensor, if I'm not checking that the sensor quality is good right at the time I receive it, and I wait until I throw it into Hadoop, and I got 1 million data streams going into Hadoop, and I'm cleaning it in Hadoop, that problem's a heck of a lot harder than if I did it right when I saw and analyzed the data when I picked it up. So there's a whole series of things where you should have an intelligent edge. So my name's Tom Arthur. I work for a company called Dianomic. Full disclosure, we're 15% owned by Schneider Electric. And we got started by Pat Kennedy. How many people know of OSIsoft? Okay. So OSIsoft was founded by a gentleman, Pat Kennedy, and I mistakenly met him one day, and he convinced me to start the company. So OSIsoft builds a historian. They got about 60% market share in process manufacturing with their time series database. And the problem they had was more and more data wasn't flowing through a SCADA or the DCS. So it might have been remote assets, it might be new workloads doing ML and AI, it might be high-fidelity sensors like accelerometers or video. None of that was flowing through the DCS. And to get all that data in context, he was looking for a way to be able to collect all that data, aggregate that data, transform that data so it could go into the Pi server for any data type. And with that idea, we started the company Dianomic. And when we really looked at the problem in OT, we realized with all of these different proprietary protocols and all these different proprietary ways of do data mapping, that really the only way to tackle that data management problem in OT space was open source. The only way to really drive an open API and get all of the different vendors with all of the different protocols, all the different ways and methods of doing things is to cooperate through an open source project. And that is what FledgePOWER is. So AVEVA OSIsoft started the project with Dianomic and Google, and we were the 3 companies that contributed Fledge to Linux Foundation and started the project Fledge and FledgePOWER, and I'll talk about the differences between those in a second. So we believe that the intelligent automation for tomorrow starts at the edge, and I think I probably just explained why we believe it starts at the edge. But we also believe it's a community-driven thing. Just like IETF solved TCP/IP and brought everyone together and did reference versions of TCP/IP back in 1988, that's not how it's done in 2024. It's not IETF-driven anymore. It's open source. Code drives the world. Android won, right? Kubernetes wins. The big, huge software projects, you know, the LAMP stack. How many people know what the LAMP stack is? See, that's pretty interesting because the LAMP stack is why we're all here today. So that's Linux, Apache, MySQL, and PHP. And when Michael Coons came out and said, hey, these 4 killer projects put together make day in the life of a web application developer go, that drove the internet as much as anything. They crushed .NET, they crushed Microsoft, and that started the Linux Foundation. So OT needs its LAMP stack to consolidate the way data is gathered and managed and applications are built. That's a community. So we contributed what we call, and it's commercially called FogLamp. So I've heard of a lot of discussions around what about open source, what about support, what about who I call if something doesn't work. This has been solved in open source for a long, long, long time. You call Red Hat, you call Ubuntu, you call Google if you're Hitachi using Android. That's who you call. So we are the company that supports Fledge and FledgePOWER. And we sell a commercial version called FogLamp, and now you know why it's called LAMP. We're playing on the LAMP stack. And for those that have been around in the IoT space for a long time, Cisco called it fog computing when they talked about the edge. So you compare, you add fog computing to the LAMP stack, you get FogLamp, and that's the commercial version of Fledge and FledgePOWER. So what are the differences between them? So the project started by contributing FogLamp to the Linux Foundation umbrella group called LF Edge. So there's about a half a dozen projects at LF Edge, and Fledge is one of them. And that's the basic set of microservice code that I'll talk about here coming up shortly. And then FledgePOWER took Fledge and started, and it was mainly RTE and Oleander, started writing what we call plugins for the power industry. So things like IEC61850 for both a north and a south connection, 61850, TASE2, HNZ. We had other people supply DNP3 and Modbus. So all of the various protocols you find more in the energy marketplace were then contributed through the FledgePOWER brand. They run on Fledge, and if you want commercial support, you call Dianomic, and that's called Foglamp. Clear? One more project that might just be worth noting. How many people are familiar with Project Margo? So Margo's pretty interesting. Margo is brand new with the Linux Foundation, and it's started by Schneider, ABB, Microsoft, Capgemini, Siemens. I think Wellotech is in there, Dianomic is in there, Zadata, and there's a couple more. And their goal is to solve the orchestration problem with PCs. So how do you do secure operating system virtualization out at the edge that you then could load something like a Fledge on top of for the data path? So that's well worth looking into. So today, Fledge is going to be one of the reference applications on the Margo project. All right, a little bit of background, and you probably already have a little inkling of this. How many people are familiar with tools like Kepware? Okay, or how many people use historians and then have connectors or interfaces to get data from their transformers and SCADA systems into there? So the classic 1980 architecture in OT was simply get a connector to a protocol, get the data, and send it to this database. And that is basically the architecture you see on the left. So I can get IEC61850, I get 61850, I get Modbus, I can get DNP3, and I can send it to this database. All right, so what you end up with is a database that has all the data, of course. Then there's these new ideas that these new protocols solve everything, whether it's MQTT, Sparkplug, or OPCUA. So I'll take all these different protocols, I'll connect it to OPCUA, and I'm done. This doesn't work. What you really need in an intelligent edge is the ability to collect from any machine, any protocol, any data map, and integrate that with one or multiple destinations of any protocol. I can send it to the cloud, I can send it to the historian, I can send it to the MES system, I can send it to the maintenance system, and I can format the data with the schema necessary for the group consuming it. But not only that, I can support writes going back through the same data pipeline, so I can do things like set point control. And now that I have my millions of tags streaming through my data pipeline, I need to be able to execute applications on those data streams. That is an intelligent edge. So you can process, transform, data manage, you can integrate that data, and you can collect that data from any source. This is an actual project that I guarantee you every single person in this room has application for, because it's needed in every OT data pipeline. If you want to get away from the vendor lock and you want universal data management and you're doing any of these new kinds of workloads, you need an intelligent edge. Maybe you don't choose Fledge or FledgePOWER, but you must have one to do this work. So I've got an architecture slide at the end if we want to get into architecture, but I kind of ignored it for this presentation just because of time. So if we get there and you want to, I'll be happy to. How do you do that? But at a super, super high level, what FledgePOWER can do is we can collect data from any type of data, any protocol, any data map, and then you can, once you ingress that data, you can filter that data when you receive it. And so one of the easiest things to think about is, let's say, an accelerometer or a PMU, right? I want to do signal processing right when I receive this raw vibration data. So it can begin to transform that data right when you get it, and then it converts it to a common JSON, and from that common JSON, it converts it again into the protocol of the destination. So I can take this vibration data, I can signal process it with FFT, I could convert it to a common JSON, and then I can convert that into how you send it to Amazon, how you send it to Google, how you send it to a Pi server, how you send it to eDNA, how you send it to your IBM maintenance system. But not only that, you can create multiple pipelines to multiple destinations from a single target. And then after that, you can also put logic in these pipelines. So you can write any kind of application. It could be something as simple as converting Celsius to Fahrenheit, or something as complex as running machine learning inference on the edge. So we have time, I'm going to show you a machine learning application that we're doing with Archer Daniel Midland on centrifuges. So at a super high level, then people usually ask, well, why would I do these workloads on the edge and not in the cloud? And the first answer we'll tell you is do everything you absolutely positively can in the cloud, because cloud has so many advantages, period, stop. However, in OT, you often have latency issues, you have cost issues, you have data volume issues, you have compliance issues, networking issues, and security issues. And if those get in the way, you then need to do those transformations and that processing closer and closer to the data source, and that's what drives an intelligent edge. Any questions so far? Make sense? And so here's my one commercial slide, my only one. So Dianomic, as I said, we license a commercial version of Fledge and FledgePOWER and give support to you. We work with systems integrators, no different than any other commercial software. And we call that the FogLamp suite. So Fledge and FledgePOWER is also called FogLamp. And what is that? That is 6 microservices that run on the edge and are open source with an Apache 2 license in GitHub, governed by the Linux Foundation. So what do those 6 things do? First and foremost, the first microservice collects and integrates data from any source. The second thing a FogLamp or a Fledge does is then you can do higher fidelity data, things like vibration data, accelerometer data, vision data. You can drive applications on that edge. And then last but not least, when you start getting into machine learning and AI, there are very specific data transformations and data pipelines one needs to support in the support of data science. So I'm talking specifically around running AI and ML applications where inference is on the edge. And when inference is on the edge, you need to have a way to migrate models that have now been tested by, first you need to, the whole life cycle, you need to be able to get the data to the data scientist, you need to be able to get the labels, you need to be able to get the data clean to the data science, they build the model with the tool of choice, they then take that model, they distribute that model out to the compute on the edge, where they execute an application that's tied into operations somehow. So the data pipelines to get the data there, and the data pipelines to get the models back, and abstract that whole thing away from operations so data science can be data science, while operators can be operators. So it supports that. And then the way we make a living is we license a commercial-only product called FogLamp Manage. So when you have hundreds or thousands or tens of thousands of data pipelines out in the field, how do you do updates, deletes, rollbacks? How do you do lifecycle management? How do you do configuration management? How do you do templating? So that's FogLamp Manage to manage thousands of data pipelines. So now I'm going to go into some use cases. So this was a demo we did at Distributech. And what you're looking at here was a Schneider P5 relay. It's not used by large energy companies. It's used by large industrials on their plant floor. So it was a P5 relay. It supported 61850 DNP3 and Modbus. And what we demonstrated was taking a 61850 SCL file, and we put it into FogLamp and put it into Fledge, and we parsed that file to describe the data definition from that P5 into the schema format of their Pi server. So we completely automated the data transformation to the schema from SCL files into a Pi, what's called AF, their AF attribute, which is where their hierarchy schema sits in a Pi server. But not only that, we took the data definitions of the 61850, and we took the tags and the values and the naming convention, and we applied 61850 to DNP3 and Modbus. and completely automated DNP3 and Modbus tags also into the historian. That's an intelligent edge. Make sense? So you have your SCT, create an SCL file, send an SCL file to Fledge. Fledge created the data pipelines from that file back to the historian and the EMS system. Use case number 1. Use case number 2, and I'm hoping to be able to say who the name is in 2 weeks, but it's a large federal government, US federal government energy company, and their need is they have an old historian called eDNA, and they are migrating that to a new historian and to the cloud. And so out in their substations, 600 substations, they have Modbus, DNP3, and SNMP devices that are sending tag values, data, to eDNA. Now they have about 600 applications they've written over 10 years to eDNA, but eDNA is going away and they're migrating to a Pi server. So what they needed to do was keep their eDNA infrastructure alive for 2 years while they migrate those 600 applications to the new historian. Everyone who has a historian and is migrating to the cloud or migrating their infrastructure, so whether you're migrating on your client side, IEC61850 SCL, DNP3, Modbus 61850, if you're migrating on that side, which will be the RTE use case I show you, or you're migrating on the integration side, the historian you're using, the maintenance system you're using, the cloud system you're using, you need data pipelines that support these migrations over time that manage your data. So this enabled them to keep eDNA alive for 2 years during the time of migrating those applications to the new historian, all in the same data pipelines. Make sense? Our very first customer was Jacksonville Energy Authority. They're the 8th largest utility in the United States. So they're an energy company, wastewater, as well as just water. So water, wastewater, and energy. And they're using FledgePOWER in their IIoT infrastructure. So I'm going to talk about RTE using it in SCADA. In this case, they're not using it in SCADA. They're using it for their maintenance team. So their maintenance team had a whole bunch of different condition monitoring services that they wanted, that the operators on SCADA didn't have the points to do. And so they built a parallel network to connect going from top to bottom. So IECA and ADS, they do manhole monitoring, so various parameters of a manhole, water buildup, moisture, and so forth, and they're reporting that back. So one of those uses a REST API, one uses Modbus. They're using infrared cameras in substations to detect heat buildup in various assets. If you kind of go down, their SCADA battery backup system using OPCUA. You keep going down, the Dynamic, the Qualitrol, and the Vasala, those are all different instruments they use to monitor transformer health, from heat buildup, oil problems, to gas buildup. And when you go down below, they're circuit breaker monitors, and as well as just generic I/O, because as you know, points are very expensive on your SCADA. So for generic 420 milliamp sensors, 20% the cost. And so they're taking all of that monitoring in their substation on a parallel network to SCADA, and they're sending it to their historian and sending it to AWS, all with Fledge. All right, it's with RTE here, it always feels weird for me to give the presentation. So this is a presentation RTE gave, and so it's their PowerPoint on it. And I'm going to probably just let the PowerPoint speak for itself instead of me talking, unless anyone from RTE in here wants to give it. But I'll give it my best shot. So they're looking at really their next generation control system, but what they're really doing here is they're having older substations using IEC104, using TASE2, using HNZ. These are different protocols used in different substation infrastructure, and they have a new EMS system, and they need the ability to have the older protocols and the newer protocols cooperate, as well as the set point controls coming back from their EMS. And so Fledge takes care of the pipeline both directions as a multi-protocol gateway. So why? Well, better flexibility and scalability than the older systems, reduced maintenance costs, an open and standardized model, it allows them to migrate to 61850 over time. Everybody has that problem. Facilitate the integration of renewable energies. So it solves all of those problems by an intelligent data pipeline from legacy systems to new systems on both the integration and the collection side. So this is their graph. So what they actually have is, I think for every 150 substations, they have a FLEDGE, and then each one of those gets aggregated. So you have 150 substations connected to the RTUs, 150 FledgePOWERs that then aggregate to a single FledgePOWER that then goes to their SCADA and their automation data center. And that's basically the new architecture. Now they've deployed so far in 8 substations. And the plan is, and you should probably ask them, was to, I think, have about 600 done by next year. And so exactly what is the data? So it actually is 118 set point commands going back down to the RTUs, and the data going up is 317 status points and 17 measurements per substation flowing through those data pipelines. And they vision exactly what I've kind of already talked about, with JEA, and I talked about with the federal government one, many different types of applications where connecting brownfield to greenfield on both the collection side and the integration side enables their data management. It's across the whole business. So FledgePOWER then was really started with RTE taking Fledge, and as I already said, writing, so they have a team of software engineers that started writing IEC61850. So Fledge has what's called a plug-in architecture, so simply through a configuration, you can change it from a Modbus integration to a DNP3 integration to a 104 integration to a 61850. So that's just through a configuration change. So they write these plugins, an IEC61850 plugin, so now it supports IEC61850 for ingress and egress. They wrote a TASE2 for ingress and egress. They wrote a 61850. So what's cool about this plug-in architecture is they just focused on the job in front of them, a new protocol, and everything else Fledge does just works through its microservice architecture. And I think I might have time here to show you the architecture and how that actually works. So this was their contribution. And then they also have what they call pivot tables, which are filters in FledgePOWER that do the translation of a set point control coming back the other way. So how do I translate a 61850 set point command into a 104 set point command on the other end? So it's both directions. And that too then was contributed to the project. And I got one more use case having nothing to do with energy, but it's just a cool use case, so I'll talk about it. How many people have heard of Archer Daniel Midland? No? Okay. Cargill? So Cargill is the largest private company in the United States, about $200 billion food processing. ADM's their biggest competitor. So this is a public use case with Archer Daniel Midland. They produce biodiesel. They produce corn oil, soybean oil, food products, animal food products. And in the production of canola oil and biodiesel, they use an industrial centrifuge at the last step to purify it. So you take a soybean, you crush it, you emulsify it with water, you run it through a filter, and then it comes streaming through into this big centrifuge about the size of a car. And out the middle of the centrifuge is the light oil. At about 30 degrees on the centrifuge is something called lecithin. It's used in food thickener. It's gross. I didn't even know what it was. You don't want to know either. And then out the edge, they actually do this activity called a chute, which is the water and the last particles. And so that's the last piece of filtering food oil before it hits your grocery store shelf. So in a centrifuge that's not working on batches, it's working to flows, there's a problem called a breakover. And a breakover is when the light oil mixes with the lecithin and it's right on that edge, and so you're not doing your separation very well anymore. So the theory was, could we build a machine learning model using the PLC data from the centrifuge and 4 accelerometers to predict a breakover a minute before it happens using ML and alert the operator to do a large chute to prevent it. And that increases gross margin, less maintenance, and all goodness for higher quality oil. And it worked. So how'd that happen? So just 2 seconds on ML for those that aren't familiar kind of with the steps. And I'm talking about edge ML for machine condition monitoring, where inference is running on the edge in compute right next to the machine. So the first cycle in ML is, of course, get the data for the data scientist, make sure it's clean data, do all the data labeling. So the basic data management starts right at the collection. Send that to the tool of choice. In this case, it's Google Cloud. We're using Vertex with an autoencoder. Build a model. Now the model, test the model, and then you distribute the model to the compute engine that is next to the centrifuge. And then it runs with the application operationally to send alerts to say, hey, you're about to get a breakover. Make sense? So with, it says fog lamp, but all this code is in Fledge and FledgePOWER as well. Here's exactly what it's doing. So we connect to Ethernet IP, so protocol of choice. It has its own unique data mapping, so we transform and understand that data mapping. And then we have 4 accelerometers on that exact same machine. So we now have raw vibration data coming in at 20 kilohertz. So the first step there is we do signal processing on the edge, FFT, RMS, low band, high band filtering. And then we do something called gating. So it's interesting to get vibration data, but I want the vibration data to have the label of what the machine was doing at the time. So we take the 2 data pipelines right on the edge, and we see here's the RPM, here's the heat, here's how the valves were set coming in and coming out of the centrifuge, and we automatically begin labeling the accelerometer data, saying here's what the machine was doing when it was vibrating like that. And so we send all of that label clean data then to the data scientist over here, which is in Google Cloud. They build the model. We then use our tool, which is the commercial part that we make a living on, Fog Lamp Manage. We distribute that model out to the Fledge Fog Lamp out on the edge, running on an Advantech gateway right next to the centrifuge. So now we have a breakover detection application sitting next to a centrifuge. And now when we see the vibration and all the parameters of the PLC that predict a breakover, we've integrated that alert into their Pi server, which is the HMI of the operator, and say, hey, you're about to get a breakover, and he can do the large shoot and prevent it. So that is a machine learning intelligent edge with an open source project available to everyone in this room. How much time do we have? When was this? I got 10 more minutes? So let's do a quick architecture slide, and this will be my last slide. So how does it actually work, I guess, for the computer guys in the room here? So what is FledgePOWER? It is literally 6 microservices that run in Linux, and they can run on bare metal, it can run in a virtual machine, or it can be containerized. We've tested it with things like Kubernetes, with Rancher, with Zadata. Like I said, we'll be testing it with Margo and different orchestration tools. Pretty much, you know, it's a modern cloud architecture, microservice based. So each of these green boxes you see are a unique microservice. The blue boxes are what we call plugins, and that's what RTE built. RTE built an IEC61850 plugin for the South. So what you see here now is, if I start on the South, this is where data comes into FledgePOWER. So it ingresses through the South service, and you simply configure what is your protocol. So I got IEC61850 RTU. I'm going to configure it for that. And then the other blue box is on the right. You may want to filter data right when you receive it. So examples were like I gave on the centrifuge. I'm not going to send raw vibration data. That's actually, it was 12 gigabytes of vibration data a day from that centrifuge. I'm not sending that to AWS for some data scientist to play with. I'm going to do lots of filtering before I send it there. So you can filter your data in that South service, and then it passes to the next microservice, which is the storage service. So we convert that IEC61850 or that accelerometer data into a common JSON format, either in SQLite or in Postgres. And that's in the storage service then, where we can buffer the data so you won't lose any in case you're in some environment, which is common in OT, where you have an unreliable network or any kind of those issues. So we don't want to lose any data. Convert it to a common JSON, store it in memory or store it in Postgres. And then from the storage service, we pass it to the north microservice, and you can see it basically mirrors the south. So this is how we integrate data to any destination. And so in this case, you might want to send it to, let's say, a Pi server that uses the OMF format, OSI message format, or you might send it to Google Cloud to the data scientist, or in our case with that centrifuge, we sent it to both. So we had a configuration integrating that data for the data scientist with a specific data transformation for data science, which was unique from the transformations we did to match the schema in their historian from the exact same data sources. So we have now a complex pipeline management system, multiple inputs, multiple outputs. You can have different security and different transformations defined in each of these pipelines. Any questions so far? So those are the first 3 microservices. Yeah.
What's the interface between the microservices?
REST. It's all REST API.
But you can put all the microservices in a different data.
You can. And you can even split them. You can have multiple souths running against it, or you can have multiple norths. So what you probably have in mind right now is this kind of one-to-one mapping, but no, it can be one to many or many to one. It's just the way AWS works. And so then the 4th microservice is set point control. So you have the ability to write back to the south service, and those write commands can come from the north, and they can come from the next microservice I'm going to talk about, or they can actually come from logic sitting in the south. So you can leverage that and do writes back. So like in RTE's case, they have these pivot files that are translating a 61850 into a 104 set point. That's all done in the set point control service. The 5th one is the event service, and it's exactly as you expect. You can set up any kind of application logic. I mean, this is open source, Apache 2. You can write in Python, you can write in C. I should have said at the beginning, all the plugins are written in Python if you want, or C++ if you need performance. And there's tons of example code on the documentation and all that to help you do that. And RTE did fantastic. They jumped on it and got it done. I think they wrote most of theirs in Python. And then, so you can write up any kind of logic. You can do events and actions. So you can send an event manager. You can do quality checks. So like on the centrifuge, we're doing standard deviation views of all the sine waves coming in, and we can alert when we suspect a sensor is bad. You can do that right when you get the data. And then last, of course, is orchestration. How do you manage a fog lamp? How do you do configuration lifecycle, update, delete, monitor it, monitor those pipelines and so forth. And all of that is accessed through an open published REST API. And it's that open published REST API that Fog Lamp Manage talks to. So you could come to us and license something if you want to scale it all up, or it's open and published and you can write your own to any kind of REST interface scripting that you have in mind. And so in a nutshell, that is the architecture. Mm-hmm. All of it. All of it is FledgePOWER, and Fog Lamp. There's only about 5 plugins that make Fog Lamp itself a little bit different. So one of them is probably not relevant to this room, but we sometimes go to large database systems like an OSIsoft Pi Historian, and we can make a Pi Historian a data source. So you can have your historian that's already aggregated all of your SCADA data, and we can give you an OPCUA or an MQTT real-time stream out. Send that data anywhere or even run workloads against it. So that one's in Fog Lamp, not in Fledge. But other than that, everything's in Fledge and FledgePOWER. Uh-huh.
If I receive, for example, the data within the OPCUA from the south service,
Uh-huh. Yeah, absolutely. That's like Fledge 101, very common. He was asking if you could change schema. Let's say I'm getting from OPCUA and I'm sending it to this database. Could I change the schema to this database automatically? So one of the very first things we did was Koch Industries is a customer, and it was converting REST APIs into their asset framework schema, but automatically. So by reading the REST calls, we were able to automatically give them the schema of their historian without them doing anything.
We have a SCADA system. Do you support
So I'm not sure I got it. It's 4 times redundant?
4 times redundant, yeah, computation.
Well, I'm going to say right now I don't know, because I don't know enough about the back end. But you can run 2 Fledges in parallel, and you can get HA in them and have them automatically fail over. So I imagine in that kind of configuration we could figure something out. But we'd have to look at it. Would be my answer right now. Uh-huh.
Yeah, how many RTUs or substations or anything like that use FledgePOWER
In production, there are, on the IIoT side at JEA, are about 32. And then at RTE, my understanding right now, they're at about 8 to a dozen with planned 600 by end of next year. At the account that I didn't tell you the name, I just said it's a large government one, that should be 600 by the end of the year.
Why is there a difference between north and south? Because information don't go to
Yeah.
I understand
That's actually a really good question, and it probably is as much about history, because with set point control, it goes both directions. I'm sure there's some nuance that I don't know if we actually mark the architect on exactly why, but they are roughly parallel, and there are many examples where you could do your filtering at either spot. But for instance, I can think of a couple filters that do matter. So like if I'm doing compression, I'm likely doing compression before I integrate it with a destination. I'm probably not doing compression as I'm pushing it back down. So there's filters like that. I think that north-south makes sense. But the architecture, as you see, is parallel. Yeah. We have another feature on the north we call condition forwarding, which is really cool for machine learning. So only send the data if this condition exists. So we do that actually on the centrifuge one. So the hardest part in ML that I've found is finding the subject matter expert to help me get the labels. And getting a subject matter expert on a centrifuge that says, why did I do this? And getting the label on that data during that event is by far the hardest part. So let's say so we're learning what breakovers are and reasons for breakovers. So I want to catch vibration data at a breakover. So the operator said that was a breakover. So I want to be able to buffer raw vibration data, the previous 10 minutes before the breakover and the 10 minutes past. And I'm only going to send that vibration data to the data scientist if it was around the breakover event. So that would be condition forwarding. And so a filter like that exists in the north. Uh-huh. Uh-huh. Yeah, your security is usually defined by the source and the destination of the data. Like Modbus doesn't have it. Later DNP3 does have certificates. So usually the plugin needs to support whatever the north and south security is. And what's interesting about that question too, because often it's different. So, I might have no security on Modbus, I might have a new DNP3 using a certificate, and then up north I might be using a token to send it to my historian, but I might be using this root of trust to send it to the cloud. So how do I manage 4 different security parameters on really what essentially is one data pipeline? And that's actually what FogLamp Manage does very well. But it's all REST, so it's all HTTPS between microservices. Uh-huh.
Is there a limit on the amount of data?
Well, there's so many answers to that question. So my quick answer is no. And the reason it's no is the same reason we're called Dianomic. So Dianomi in Latin means distributed. So the name of our company is Distributed Systems, Inc. And so what is this? This is, everything that made cloud computing cool is not cool about this, right? Now I've got hardware, I've got orchestration, I got a painful compute out here. Reminds me of local area networking, 1990, right? I thought I got away from that. But since it's a distributed computing environment, you can distribute your data ingress and you can distribute your egress, and that's pretty much infinite in terms of data. So there's the question about a system question, no limits. Then there's, of course, how big the container is that you stuck it in, and the type of workload going through a single data pipeline is a whole nother question. Well, Kafka and brokers, pub subs are common plugins. So like on the north, you have MQTT, MQTT Sparkplug, OPCUA, Kafka. They're all available in Fledge today. Uh-huh. Uh-huh. Yep. In the filters. So where I say that where I have the filters like FFT, image class, and so forth, so you have your data coming in, and then you can set up filters. And so that is where a data transformation, where I'm going to read the data, I'm going to transform it to this schema, and then I'm going to pass it to, and you can do it before JSON, or you could do it after JSON. It doesn't care. There's many, so when you go to the documentation, the first one I would look up OMF hints, and you'll have 50 pages of how it works, but it'd be the exact same way you would do it in exactly your question, like OPCUA to Kafka. There is no usual, since it runs, since it's just microservices. We've tested it, and we do test it on Raspberry Pi Zeros as a footprint. But since you can containerize it, we have probably 30% of our implementations are actually implemented in the cloud. So a really common one for lots of industrials is they have different services companies, doing like route-based monitoring and so forth, and that data usually is available through a REST API. So if you're going to do a REST API integration to like a historian or an MES, it's usually pretty convenient to do that in the cloud. If you saw the JEA use case, there were like 4 of them that said REST APIs. So that's how they were done. A really cool use case we have going right now is, how many people heard of SKF? Cool. So SKF, if you don't know it, they're a Swedish company. They're the largest supplier of ball bearings on planet Earth. And they have a service called Observer. So when you're a railroad company or whatever, you've bought their ball bearings, they'll do condition monitoring on lubrication and ball bearings. So like in paper mills, it's like super important. So we've done several paper mill installations with them where we've integrated Observer. So they're putting accelerometers out on these paper mills that are monitoring ball bearings, and then we integrated the PLCs of the paper mill. And so now we have PLC data, we have ball bearing health data through a REST API, and we've integrated that into the operational historian systems of the paper mill operators. And so it's the first time they got that exact same data. So that was all done through cloud. Okay, any other questions? Well, thank you for coming and all the great questions. So this was fun. Thank you.